Hello. In this lecture, we will study about Taylor series, which is a method of approximating functions. The general expression of a Taylor series expansion is given as follows. Fx is fx0 plus x minus x0 times f prime x0, that's the first derivative, plus x minus x0 squared over 2 factorial times f second derivative at x0, and then plus x minus x0 to the power 3 over 3 factorial times the third derivative of f at x0. And so this is an infinite series, it goes on. So the nth term is x minus x0 to the power n divided by n factorial times nth derivative at x0 Now this is called the Taylor's theorem. So that's the Taylor's theorem. You should know the Taylor's theorem. It is very easy. It has a very nice pattern there. Fx is fx0 plus x minus x0 to the power n over n factorial times f nth derivative of f at x0. All you had to do is give values 1, 2, 3 like that to the term n. Now this is an approximation of a function. For example, the first approximation is fx0, just one value. Second approximation is the first two. That will be the third approximation. If you add this one, the fourth approximation, and if you have n term, that will be the n n plus 1 that approximation, considering you have n term plus fx0. Now we will do an example that should make it very clear. So we will do an example where we will expand cos x first. So that is example 1 in the lecture notes using Taylor series. Then we will expand e to the power x. We already know for e to the power x what is the answer, so we will just use Taylor series to see how it works. Alright. In this example, we are going to expand cos x using Taylor series. Basically, we will use fx is cos x, and then we have just follow this formula. The first question is, what is x0? x0 is 0, so that is our assumption. So we just basically have to take different derivatives of fx. Let's do that first. First derivative of x is minus sine x. So if I apply x0 from this, I can say f prime x0 is sine 0 is 0. If second derivative of x is minus cos x, from this f2 x0 is cos 0 is 1 minus cos 0 is minus 1. Then f3x, third derivative, is sine x. From this f3 x0 is 0. f4 x is cos x. From this f4 x0 is 1. And then once again the cycle is going to repeat. f5x is minus sine x. From this f5 x0 is 0. So you can see f6 x0, f7 x0, f8 x0, are the same values as before. 0, minus 1, 0, 1 is always going to be 0, minus 1, 0, 1, 0, minus 1, 0, 1. We see a pattern. That is how it's going to repeat. So we have the values that we need to write. So all we had to do is substitute here. So when we do that, fx cos x is, if you just take each values there and substitute, you will get cos x is 1 minus x squared over 2 factorial plus x4 over 4 factorial minus x6 over 6 factorial and so on. The nth term, if you just after careful thinking, you will see it will be x to the power 2n minus 1 to the power n, x to the power 2n over 2n factorial. So if you want to check, so let's say n is equal to 1. So n is equal to 1, that will be minus 1 to the power 1 is minus 1, and then x to the power 2n, x2 over 2n factorial is 2 factorial. So that corresponds to n is equal to 1. Now if n is equal to 2, minus 1 to the power 2 is plus 1, 1 minus x to the power 2, so n is equal to 2, right? So n is equal to 2 here, x to the power 2 times 2, x4 over 2 times 2, 4 factorial. So that is n is equal to 2. So this is n is equal to 1, this is n is equal to 2, that is for n is equal to 3, and so on. So that is for n is equal to n. So that's an expansion of cos x using Taylor series. Okay, now we saw that we derived an approximation for cos x using Taylor series expansion. Now let's test it. So I'm going to use cos pi by 4 to test it. In this red box, I'm showing the exact, well, not exact value, but very good approximation for cos pi by 4. I got it from, that is this what we are seeing is accurate. So that is cos pi by 4 is 0.707106781186548. So knowing that, let's use one term, two term approximations of cos pi by 4. So the first approximation is obviously 1. I didn't write that. The second approximation is, so let me write it. The first approximation is cos pi by 4 is 1 if I just do the first term. That's a very, I would say, bad approximation because the cos pi by 4 is 0.707. Second approximation, 1 minus pi by 4 squared over 2 factorial comes down to 0.69. We are getting closer. Third approximation, if I use the 3 terms, that will be 0.7074, getting closer. And the fourth approximation is 1, if I use all 4 terms, it is 0.7071. So as you see, when we use more terms, we are getting closer and closer to the true value. So that's, we already seen that for e to the power x. So that should give a good understanding of what is the function approximation. And here we are using Taylor series for function approximation. There are other applications of Taylor series which we are going to talk about in a while. Similar to how we approximated cos x using Taylor series, now let's do another example. Expressing fx is equal to e to the power x as using Taylor series. The good thing about e to the power x is every derivative of first derivative, second derivative, third derivative, all of them is e to the power x. And then if we expand it for around x0 is equal to 0, so we are expanding around 0, then if we set x0 is equal to 0, then fx0 for all those values is equal to 1. So with that, we can go to the Taylor series expression and substitute. So x0 is 1, we have to substitute as x0 is 1 in equation 1, and then fx0 is 1, f prime x0 is 1, f second derivative x0 is 1, so all the way, all these values are 1. This is 1, this is 1, this is 1, and this is 1. All of these are 1. So the e to the power x reduces to 1 plus x squared over 2 factorial, x cubed over 3 factorial, and so on. So it is shown in equation 3. That is how we use Taylor series to expand or approximate e to the power x as an infinite series. You can test this by giving, for example, the first approximation of e to the power x is 1, second approximation is 1 plus x, and so on. We saw that the Taylor series expansion is an approximation. If you use one term, two term, as you use more terms, we get closer to the true value of the function. For example, think about e to the power x one more time. E to the power x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. If you use, as you get more terms, it becomes better and better approximation. So there is definitely an error, an approximation error involved. How much is the error? In this previous lecture, we used a method of doing this approximation to a certain number of significant digits. So we said, if the error, relative percent of error epsilon a, if we do this iteration, if we keep on increasing the term and computing the epsilon a to a point that epsilon a becomes less than epsilon s, then we can assure that we can be certain that the error is less than, it is approximate to like 3 significant digits. You can select epsilon as such that we can make the approximation that is valid for a certain number of significant digits. The Lagrange remainder is a slightly different concept where, given an approximation, for example, let's say we approximate fx using two terms. Using first term fx0 plus x minus x0 times f prime x0. Let me also use, let's say that's how I approximate. I use two-term approximation. And then how much is the error? Where can the error be? Will the error be 100? Is it 10? Is it 0.1? The question is, if I use two terms to approximate a function, how much is the error? What is the magnitude of the error? That is answered by Lagrange remainder. So the Lagrange theorem says the error will be this much, shown in equation 5. So wherever you, for example, so it is n plus 1. So we stopped at, in this example, here I stopped at two terms. The error will be R2, that will be x minus x0. So n was 1, so that will be 2 over 2 factorial f2 psi, where psi is the value. Psi can be any value between x0 and x. So you had to select a psi for worst case value. you had to take all the possible values of psi and select the one that is, because we want to see the worst case of error. That is the useful information. We don't want to know, okay, what is the smallest possible error. We want to see what is the largest possible error, so that we will have a good idea of how good our approximation is. Let me give an example about Lagrange remainder. Let's say we want to compute e to the power x. We want to approximate e to the power x using 3 terms. That is up to n is equal to 2. And let's say we want to know what is the error. The maximum error, or then a measure of error, is given by Lagrange remainder. That is R2, since it is n is equal to 2, that is why we have R2. That once we have this approximation, where will there be the error? So that is the Lagrange theorem. So that error will be anywhere in the range of x to the power 2 plus 1, because n is equal to e to the power psi divided by 2 plus 1 factorial. So psi can be anywhere between 0 and x. So if we want to see the worst case error, we will put a value that makes the error higher, the highest possible. So I will put x, because e to the power 0, that's the deciding factor. Everything else is same. So psi takes a range. So if you just think about e to the power x, if you just think about the function e to the power x, it is something like this. E to the power x, e to the power x. So when x is equal to 0, it is small, and with values greater than x, it increases. So at least for x greater than 0, I would select x to be the worst case scenario. So that's already a condition there, and it cannot be negative. If it's negative, it's going to be slightly less than that. So I select x for psi. So that makes the error, the worst case error for positive x, to be x to the power cube times e to the power x divided by 3 factorial. Now let's check. Let's assume x is equal to 0.5. So e to the power 0.5 using 3 terms is 1 plus 0.5 plus 0.5 squared over 2 factorial. That comes to 1.625. Now R2, using the same formula that is here, using the same formula, will be 0.5 to the power 3 times e to the power 0.5 divided by 3 factorial. That comes down to 0.034348, worst case error. And then true e to the power 0.5 can be computed using your calculator, which is good enough for other softwares. Even you can Google it. E to the 0.5 is true value, very close to true, is 1.648721. So true minus the value that we computed is 0.023721. So if you look at this, and this is our worst case error, and this is the real error. So the worst case error will be always slightly greater than the error that we have. So the worst case error tells us, this is the worst that could be when you use this approximation to this many terms. One of the applications of Taylor series is function approximation. Here's an example. In example 5, we should try this example. So this is like an imagined function. So that's, whereas the real use of Taylor series is to expand cos x, e to the power x, and function that are not definite, that only can be represented using an infinite series. Whereas this is an example where this is a definite function which is given by equation 15. So what we are doing in this example, I want you to try this, is we are just doing the first order approximation, n is equal to 1. What is the approximate function? What is the first order approximation of this? And then what is the second order, and things like that. So the first order approximation of this function, the original function is in equation 5. if you follow Taylor series method, the first order approximation will come down to just 1.2, zeroth order. The first order will be 1.2 minus 0.25 x. The second order, third order, fourth order. You will see we recover the whole function using the fourth order approximation. So it is like a TOE example to understand a little bit more about the application of Taylor series as an approximation, a function approximation. Now, the use case is always already explained here using approximating e to the power x, approximating cos x, things like that. That is exactly how these cos x is. For example, when you type cos x, cos 0.2 in your computer, that computer uses an approximation like this to compute the value. The value is very accurate because they use many terms, many more terms. We only do 2-3 terms, whereas they will use, I don't know, 50 terms, things like that. So with this, one of the applications of Taylor series is concluded. Next, I will talk about another application of Taylor series in numerical difference. An application of Taylor series is going to be discussed now. Let us review the original Taylor series formula a little bit. The one I show here, that's the original Taylor series formula. Fx is fx0 plus x minus x0 times f prime x0 and so on. So what we are doing here in so far, what we did was, if we know the function at x0, if we know the function and the values of its derivative at x0, we can express it at a point x. So we know the function as well as all its derivative at this point, and then we approximate that function here because there's no other way to approximate, because we know what is cos 0 for sure. Cos 0 is 1, but cos 0.1 we don't know. So we can use Taylor series to find cos 0.1. So that's an example. So here that we approximate. Now instead of x0, let us say xi, a present value, and then x instead of x. So substitute xi for x0 and then xi plus 1 for x. Then using this notation, we can write with the understanding that is there. Sorry. With this understanding here, we can write equation 18. That is, if you look at it, equation 18 is basically Taylor series expansion, but written instead of x0 I'm using xi, instead of x I'm using xi plus 1, and we get this. So given two consecutive values, let's say in the x-axis, then we get this formula in 18. Now if you subtract to one side, that will be f xi plus 1 minus fxi divided by age is what we will get for f prime xi. And then there is a term, there will be an error term for representing the error. So that is how you can approximate the different, the derivative of a function. So if you have a function and you don't know the derivative of function, if you know the value of that function at certain x, and if you know the value of that function at an adjacent point I plus 1, then using that you can compute the derivative of the function. We can write these xi and xi plus 1 in different ways, and we can come up with different formulas for derivative of a function. That is what's shown in equation 19, 21, and 22. And that will result in 3 different types of approximation for derivative of a function. The first one is called forward difference, second one is called backward difference, and the third one is called centered difference approximation. We will this will also be revisited later, but I would encourage you to read the book on this topic to get some more insight. The book has a lot of examples on these different ways to approximate a function. And these three, now the 5 questions are shown here in the lecture notes are assigned as homework 3, I believe. Thank you.